two speakers, and we'll start with Michael Perlman's talk. Michael Perlman, I think, is well known because of many things, because of his articles, but also because of two things in particular. I think one is that he was editor of the Annals of Statistics. And the second thing, which I happen to be particularly familiar with, is that Michael Perlman was chairman, longtime chairman of the Department of Statistics at the University of Washington, where I was fortunate to visit. He was the founder and builder of a very fine department. We will hear Professor Perlman's talk, which is given the title, let me see, Perlman. On the consistency of invariant multivariate tests.
Thank you very much. I'd like to add my thanks to those of the other speakers and participants, to the organizers of this wonderful meeting. It's really a pleasure to be here. I think Professor Arjas neglected to mention my most notable accomplishment, which was in 1968, spending a year in Minnesota with George Stein, which a place at that time had a dearth of three-star restaurants. George was not in the best mood in those days, and I did my best to cheer him up.
My close friends.
Is it possible to turn out those lights?
Any experts here?
Thank you. Thank you, Terry.
Obviously have those in Australia, don't they?
My talk today, incidentally, reflects joint work with Professor Anderson at Stanford University. Take yourself back in time to the glorious years of classical multivariate analysis, 1986 perhaps. In particular, visualize Professor Anderson's book, classic work in multivariate statistical analysis, more specifically yet Chapter 8 on the multivariate linear regression model, which I will remind you has this general form. This is simply the classical multivariate linear model, a matrix of observations, each column of Z being multivariate normal with covariance matrix sigma. The mean structure is of this form, beta times Z times D, D a design matrix. The classical testing problem in this model is that of testing that beta 1, say, is 0, or more generally a specified value, where beta 1 is a collection of rows of the parameter matrix beta. You might interpret this as the hypothesis that the first few factors in the design, the temperature, the pressure of a steel manufacturing process, play no role in the resulting observations. I'll refer you to Chapter 8 again of Anderson's book for the context of this problem. You don't have to remember this. I'm going to immediately pass to a convenient canonical form. By reparametrizing, applying non-singular linear transformations, reduce the testing problem to one involving two independent random matrices, X and Y, both multivariate normal random matrices, again, mutually independent columns, common covariance matrix sigma. The first matrix X, random matrix X, has a mean matrix C. The hypothesis becomes testing C equals 0 versus C not equal 0. Again, just the very classical multivariate testing problem. Invariance, this problem remains invariant under non-singular transformations, matrix transformations B on the left, and separate orthogonal transformations psi1 and psi2 on the right. The parameter xi and sigma are transformed accordingly, and this leads to a representation of the maximal invariance statistics and parameter. I have two equivalent representations of the maximal invariance statistic, the vector C, consisting of the ordered eigenvalues or characteristic roots of the matrix XX transpose, in effect divided by YY transpose. This reduces to the ordinary F statistic if we were dealing with dimension 1. And equivalently, we could take a one-to-one transformation from C to the vector D, where DI is the ith characteristic root of XX transpose divided by this matrix. This is the beta form. This is the F form. The non-centrality parameters, the maximum invariant parameters, which I call lambdas here, are the eigenvalues, characteristic roots of xi transpose divided by sigma. The number of these, T, incidentally, is the minimum of P and R, where P and R are the dimensions of the matrix xi which we're testing. I wish I could leave this up for your reference. This is the form of the problem with which we'll be dealing. Now, if we decide to base our decisions, our tests on the maximum invariant statistics, which I'll usually work with the beta form, the D vector, then the hypothesis can be expressed in terms of the non-centrality parameters as follows. The null hypothesis becomes that of testing lambda, the lambda vector, equals the 0 vector, against the alternative that lambda is not 0, that at least one non-centrality parameter is positive. The picture is this. We're dealing with ordered characteristic roots. So for t equals 2, the parameter space would be that wedge. The null hypothesis H0 is the origin. The alternative is everything above, but in the shaded region. And again, intuitively, we want to accept the null hypothesis or reject it for small, accordingly large values of the, I'll work with d's of d1 through dt. Again, the relation between the d's and the c's stands there. In particular, the d's are bounded between 0 and 1. So a test of hypothesis of this form would have an acceptance region, rejection region as pictured there. The key is that we accept if the d's are small, close in the neighborhood of 0, we reject if not. Well, in particular, for the reason I'm about to mention, it is monotone acceptance regions determined by monotone test statistics, to which we can restrict attention. A monotone test statistic, f, a function of these beta type statistics, d1 through dt, is called monotone if it's increasing, non-decreasing, that is, in each di. We would accept the null hypothesis if this test statistic is less than or equal to an appropriate critical value, c sub alpha, depending on alpha, the level of significance desired, and the parameters p, r, and n. P and r being the dimension of the matrix means we're testing, n the degrees of freedom of the estimate of sigma. Now, the reason we can restrict consideration to monotone test statistics, which lead to monotone acceptance regions, is due to a result of Richard Schwartz in the mid-60s, a student of Jack Kiefer, a test of this this problem is admissible if and only if a test is admissible, then the acceptance region must be monotone. Ingram Olkin and I later proved that any monotone acceptance region is unbiased. So all admissible tests are unbiased. Restricting consideration to admissible tests implies you can restrict consideration to monotone acceptance regions. There are further conditions, necessary conditions for admissibility, in particular convexity as well. But today I'm going to be talking about a more elementary property than admissibility, namely consistency, which does not require convexity. Let me give some classical standard examples of monotone invariant test statistics. If f of d is d1, the largest eigenvalue of this matrix, that's referred to as the Roy statistic, then we're led to the Roy statistic. If f is the summation di divided by 1 minus di, that's the trace of xx transpose divided by yy transpose. That's the Lawley-Hotelling, and Professor Rao reminded me also Fisher, first Fisher, I suppose, trace statistic. The likelihood ratio test statistic, also called the Wilks statistic, is of this form. Fourth statistic appearing in Chapter 8 of Anderson's book is based on the sum of the DIs. That's another trace statistic. That's the Bartlett and Nanda, but usually called simply the Pillai trace statistic. All these tests are admissible. And furthermore, let me mention here that the Pillai trace test is locally most powerful among all invariant tests. It has local optimality properties. The subject of today's talk is consistency, which in effect will deal with distant alternatives. And we'll come back to this admissible test, which has local optimality properties, and compare the two. Three more statistics, which I'm not sure have names attached to them, are based on other determinants. Recall the likelihood ratio test can be written in this form: determinant of xx prime plus yy prime over determinant of yy prime. Yy transpose I could call S. It's essentially the sample covariance matrix. Other ratios of determinants that are reasonable and that they lead to monotone test statistics are number 5 and 6. And also let's consider 7, the minimum eigenvalue. I'll use those for illustrative purposes only. Let me, it's perhaps easier to get an idea of the nature of these statistics by looking at pictures of their acceptance regions. If we let A be, or A sub f, be the set of all D's for which f of D is less than C, the acceptance region based on the test statistic, the Roy test has an acceptance region of this type. The Lawley-Hotelling Fisher statistic looks like, acceptance region looks like that. The likelihood ratio test Wilks looks like that, and so on. And getting ahead of myself, I call your attention to this vertex. This is the case t equals 2, obviously. It's going to be essential for our results as to whether or not this vertex is in the acceptance region or not. It's interesting then to note that it is not in the acceptance region, it's in the rejection region for the first 3 tests. For the Pillai statistic, it is sometimes in and sometimes out. It's excluded for smaller acceptance regions. Small acceptance region corresponds to larger values of the significance level. So let's record that there. Alpha is large in this case. The other 3 statistics have these behaviors. For number 5, which you probably don't remember, we get a picture like this. Convexity is violated, therefore I've pointed out that these are inadmissible, that is, A is not convex. For C less than 1, which corresponds to large alpha, but for small significance levels, probably the ones one's interested in, admissibility, convexity, and therefore admissibility occurs. In each case, however, unlike the Pillai test, this statistic always, the acceptance region always does include, at least on its boundary, let me put it the other way. The rejection region always includes on its boundary this vertex. And that's going to be the key condition for consistency. Okay, these are pictures of 6 and 7. Now, there have been quite a bit of work all the way up through the 1970s, perhaps into the 80s, by many people. I've listed names, I've probably slighted a few people. The properties studied have been, as I've mentioned, admissibility of an acceptance test with acceptance region A, the Bayes net character of a test, its unbiasedness, monotone power functions, local properties, locally most powerful invariant, locally minimax, robustness properties. Lots of work has been done on these questions, but to our knowledge, there has been little or no work on perhaps the most elementary question, consistency. Which invariant tests for the multivariate analysis of variance are consistent, restricting ourselves to monotone acceptance regions? And that's the subject of our work. Now, there's another way of introducing this question. There is no unique admissible test in the multivariate analysis of variance. The problem is many-dimensional. I already pointed out that the first 4 test statistics are all admissible. How does one choose among competing admissible tests? Well, certainly unbiasedness does not help to reduce the candidates for consideration, because all admissible tests have monotone regions and hence are unbiased. It turns out, however, that not every admissible invariant test is consistent. Now, we have to explain that. What definition of consistency does one use to make that a true statement? I've asked the audience to guess which of these admissible tests is not consistent, but I won't take time to take a poll here. What I will do is recall the 2 definitions of the classical definition of consistency. Really concerns not a single acceptance region, but a test statistic which, as n, the degrees of freedom, moves to infinity, determines a whole sequence of acceptance regions. So the classical notion of consistency, at least in the Neyman Pearson context, says if we fix a significance level alpha between 0 and 1, and fix an alternative lambda star, choose a sequence of significance levels C sub alpha depending on n, I'll suppress the P and R, so that the probability of rejection is held fixed at alpha as n goes to infinity, then we say F is consistent, but we have to distinguish that with from another notion of consistency, so we'll call this sample size consistency. N, the degrees of freedom of the Wishart matrix S, which was YY transpose, essentially plays the role of a sample size. F is sample size consistent at a fixed alternative lambda star if for this sequence of tests, n going to infinity, the probability at the non-centrality parameter lambda equal to n times a fixed lambda star, if that power approaches 1. More generally, we could replace n lambda star by n plus little o of n times lambda star. The motivation for that is simply this. If you have in the univariate case, a sequence of independent, identically distributed normal random variables. Want to test the hypothesis mu equals 0 with unknown variance sigma squared. The usual two-sided t-test turns out to have non-centrality parameter of the form n times the mu squared divided by sigma squared. So this ratio mu squared over sigma squared plays the role of our lambda star, which is fixed, and the n appears as a multiplier. So that's why we consider this form. That's the classical definition. It's not, I've never, it turns out, looking through the literature, I couldn't find a result which gives a necessary and sufficient condition for a test statistic to lead to be sample size consistent. A theorem which we've developed, a relatively simple theorem, I've stated here. I think this is the more complex form, so let me ignore that slide and move to the next one. The criterion geometrically can be pictured as followed. This does not work for all. I gave a more general statement on the last transparency, but for test statistics f such that f0, which is the test statistic on the diagonal, that f0 of eta would be f evaluated at the point eta, 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 and so on. So it would be f evaluated on this diagonal. For test statistics such that f0 eta behaves like a power of eta in a neighborhood of 0, then sample size consistency is determined by comparing the ratio of the test statistic at a sequence of points converging to an alternative, a fixed alternative delta. I should say delta star. Delta star is lambda star, it's the beta form, lambda star over lambda star plus 1. If you look at a sequence of points approaching a fixed delta star, compare the value of the test statistic there with the value of the test statistic at the diagonal, look at the ratio. The key condition is whether or not this limit, which we've called f double tilde of delta, is either infinite or finite. If it's infinite, the test is consistent at the corresponding lambda star. If it's finite, it's inconsistent. Typically, sample size consistency depends only on the rank of the alternative, namely the number of non-zero components of the lambda star vector, or equivalently the delta star vector. So in this case, the rank would be 1. SSCI, F is SSCI means F is sample size consistent of degree I. It's sample size consistent for all fixed alternatives of rank I. Going back quickly over these examples, the set, recall the 7 examples, very simple computations for this ratio f double tilde shows that in the first 6 cases, well, in case 1, 2, 3, 4, the admissible cases, we have sample size consistency of degree 1, which means sample size consistency for alternatives of the lowest rank, and hence of all ranks. If a statistic is sample size consistent for alternatives of rank I, then it's consistent for all alternatives of rank greater than or equal to I. 5 and 6 also have sample size consistency. Test 7, which only depended on the smallest root, will not be sample size consistent, but that's not surprising. The point is that classical notion of consistency does not distinguish among invariant admissible tests. All admissible tests, statistics, are sample size consistent. So like the notion of unbiasedness, ordinary classical consistency does not serve to distinguish among invariant tests. Well, we have a new notion, however, perhaps new, of consistency which does distinguish. We've called that, for want of a better term, parameter consistent. Now, parameter consistency is in a sense a simpler property. It's defined for a fixed acceptance region A. We keep the sample size fixed. For a given n, an acceptance region is called parameter consistent of degree I if and only if the power, that's the probability of rejection, not being in the acceptance region, approaches 1 as the ith non-centrality parameter approaches infinity. Well, again, PCI, parameter consistency of degree I, implies parameter consistency for all higher degrees. Parameter consistency of degree 1 is a desirable property. That says the power approaches 1 whenever the alternative approaches infinity, whenever the alternative is distant from the null hypothesis. Now, a simple geometric condition determines parameter consistency of degree I without going over all these details. It's very simple. You look at the vertices of this region A sub t, that's the domain of the D vector, D1 up to dt. If, for example, E1, which is 1, 0, if this corner falls in the rejection region or on its boundary, outside the acceptance region, that is, or on the boundary, then we have parameter consistency of degree 1. If not, parameter consistency fails. And now you can see, recall very quickly that for these tests, the first three tests, the Roy test, the Lawley-Hotelling-Fisher test, the likelihood ratio test of Wilks, are always parameter consistent. But the Pillai-Trace test fails to be parameter consistent for small values of alpha. When this picture obtains, when this corner vertex is within the acceptance region, not on its boundary or in the rejection region, we do not have full parameter consistency. Better conclude. In particular, the Pillai test, which is admissible based on bias, locally most powerful invariant. It's been pointed out it has robustness properties. It's not parameter consistent unless alpha is sufficiently large, or equivalently, unless n, the sample size, is sufficiently large. In particular, what this means in practice is that such a test may not detect distant alternatives, infinitely far from the null hypothesis, if they are of low rank in an asymptotic sense. If the smallest non-centrality parameters are small relative to the largest non-centrality parameters. Sorry I didn't leave too much time for questions, if any. I certainly would be happy to answer questions later.